Imagine that you love building and racing toy cars. You want to see which car design is the fastest. Instead of building lots of real cars and racing them, which can be expensive and time-consuming, you create a small, pretend race on your computer. You make little digital cars that look and act like real ones and race them on a virtual track. Doing this lets you quickly figure out which car design is the fastest without having to build and race actual cars. Think about another situation. Suppose you want to build a new model of an aeroplane and fly it, but you don't know what would happen if you flew it. Instead of building the real aeroplane and risking damage, you use a computer program that simulates the aeroplane's flight. You can see if it would fly well, how high it might go, and how it would handle different conditions. These all can be assessed with the computer only. Think of a doctor who needs to learn how to perform surgery. Instead of doing surgery on a real person, which could be dangerous, the doctor can practice on a lifelike dummy called a mannequin. The mannequin behaves like a real patient. The doctor can make mistakes and learn without harming anyone. Imagine that you are a hospital manager, and you want to improve the service in your hospital to ensure that patients have a better experience. There are many parameters on which you want to work simultaneously, like overcrowding and long waiting lines of patients, movement of patients in the hospital, the process of billing, and hospital logistics like manpower and equipment. But you have very limited time and money to do so. You can create a model of your hospital which imitates all the processes of your real-world hospital. Using this model and with the help of computers only, you can understand how different factors affect services and what changes you can make to improve the service in your hospital. This way, your maximum resources will be saved. Hello everyone. Welcome to the lecture series on health management. We discussed that management methods and techniques are broadly classified into 5 categories: statistical techniques, activity analysis, mathematical techniques, financial techniques, and others or miscellaneous techniques. Mathematical techniques include techniques like simulation study or models, systems analysis, linear programming, inventory control methods, precedence and arrow diagramming, and network analysis. In this session, we will discuss the simulation study or simulation models. First, let us understand what is modeling and simulation. Modeling is the process of creating a simplified representation of a real-world system or process. These representations are called models. This model imitates a real system. In simple words, modeling is creating a model which represents a real system and its properties. Simulation is the process of using this model to study the performance of a system. You can experiment with this model by putting it in different conditions and scenarios without interacting with the real system. So, it can be said that simulation is the imitation of the operation of a real-world system or process. It can be done using a computer program, physical model, or other representation. In essence, simulation is a way to test ideas, make predictions, or learn about complex systems by creating models. History of simulation. In the 17th century, mathematicians like Blaise Pascal and Pierre de Fermat laid the groundwork for probability theory, which would later become a fundamental simulation component. During World War II, 2 mathematicians, John von Neumann and Stanislaw Ulam, were facing the puzzling problem of the behavior of neutrons. In 1940, while working on the Manhattan Project, which was the U.S. effort to develop the atomic bomb, they, along with other researchers, developed a method named Monte Carlo. This method was based on random sampling techniques to study neutron scattering. The name Monte Carlo was in reference to the Monte Carlo Casino in Monaco, which was known for games of chance and randomness. From 1940s to 1950s, development of electronic computers, such as the ENIAC and UNIVAC, provided the computational power needed for more advanced simulations. As the need for more specialized simulation tools grew, dedicated simulation languages were required. From 1960 to 1970, many special-purpose simulation languages were developed, like Simula, SimScript, and GPSS or general-purpose simulation systems. From 1970 to 1980, research was initiated on the mathematical foundations of simulation, and simulation was widely used in business and engineering. During this period, PC-based simulation software, graphical user interfaces and object-oriented programming were developed. During the 1990s, web-based simulation, fancy animated graphics, and simulation-based optimization were developed. Today, simulation techniques have been incorporated into machine learning and artificial intelligence to improve model accuracy and decision-making. Simulation is vital in various fields, including science, engineering, finance, healthcare, and social sciences. Emerging technologies like quantum computing are expected to impact the capabilities and scope of simulation in the future. Let us understand the different types of simulations. Simulations can be classified into various categories based on different criteria. Number 1, based on purpose. First is the Monte Carlo simulation. Imagine you want to estimate the chance of winning a card game but can't calculate it directly. Instead, you repeatedly play the game with random card draws and keep track of your wins. The more games you play, the closer your estimate gets to the actual probability. Monte Carlo simulation estimates outcomes under such uncertainties. It uses random sampling and probability to model and analyze complex problems. Training simulations. They are designed to train individuals or teams in specific skills, procedures, or tasks. For example, flight simulators are used to train pilots by simulating various flying conditions and scenarios to make them understand the fundamental principles of flight, aircraft controls, and emergency procedures. Research simulations. They are used for scientific research, experimentation, and hypothesis testing. For example, simulating the behavior of particles in a particle accelerator to study fundamental physics. Or, a researcher is studying the spread of a contagious disease within a population to understand how different factors affect the rate of disease transmission and how interventions like vaccination can mitigate the spread. Educational simulations. They are created for educational purposes to teach concepts, history, or principles in an interactive manner. For example, educational software that simulates historical events and allows students to explore and learn interactively. Decision-making simulations. They assist in making informed decisions by modeling scenarios and their potential outcomes. For example, business simulations help executives make strategic decisions by modeling market dynamics and competition. Financial simulation. Consider investing in the stock market. Financial simulation models how different investment strategies may perform over time. It's like running a virtual portfolio to see how your investments would grow or shrink. Number 2, based on time and event handling. Continuous simulations. These simulators model systems in which the variables change continuously over time. Such as simulating fluid flow in pipes to optimize the design of a plumbing system. Or simulation for weather forecasting. Discrete event simulations. Discrete event simulation model systems where events occur at distinct points in time. It is commonly used to study processes with discrete events, such as customer arrivals or machine breakdowns. Like modeling a manufacturing process to optimize production schedules and resource allocation, or model patients' arrival and waiting times for hospital process optimization. Hybrid simulations. These are combined elements of both continuous and discrete event simulations. This is suitable for complex systems with varying behaviors. Number 3, based on scale and detail. Microscopic simulations. Simulate individual entities and their interactions within a system, which is suitable for modeling small-scale phenomena. For example, you are simulating the behavior of individual molecules in a chemical reaction to study reaction kinetics. Macroscopic simulations. They focus on system-level behavior and aggregated data, which is ideal for large-scale scenarios. For example, modeling traffic flow on a city's road network to analyze congestion patterns. Number 4, based on interactivity. Interactive simulations. These simulations allow users to actively participate and control the simulation's parameters. These are often used for training and learning purposes. For example, virtual reality simulations for surgical training that allow trainees to perform procedures in a controlled environment. Non-interactive or passive simulations. They run without user intervention and provide results or data for analysis. This is typical in research and modeling. For example, running climate models to predict long-term weather patterns without user intervention. Number 5, based on technology. Physical simulations. They use physical models or prototypes to replicate real-world phenomena. For example, conducting crash tests using physical crash test dummies to evaluate vehicle safety. Virtual reality or VR simulations. They create immersive digital environments that users can interact with using VR technology. For example, virtual reality games and simulations that immerse users in digital environments for entertainment or training. Computer-based simulations. They run on standard computers or servers and are often used in research, training, and decision support. For example, simulating the economic scenario of a country on a computer to study the effects of different fiscal policies. Number 6, based on domain. Healthcare simulations. They are applied in medical training, patient care improvement, and disease modeling. For example, using patient simulators in medical training to practice medical procedures and improve clinical skills. Environmental simulations. To study environmental processes, climate change, and ecosystems. For example, modeling the effects of deforestation on ecosystems and climate. Business simulations. They are used for modeling market dynamics, supply chains, and business strategies. For example, running a business strategy simulation to make decisions about product development, marketing, and finances. Military and defense simulations. They simulate military operations, training, and strategy planning. For example, simulating military maneuvers and battlefield scenarios for training and strategic planning. Social simulations. They model human behavior, societal interactions, and complex adaptive systems. For example, modeling the spread of infectious diseases in a population to apprise public health interventions. Number 7, based on agent behavior. Agent-based simulations. They focus on modeling individual agents or entities within a system and their interactions. They are used in social sciences, ecology, and economics. For example, simulating the behavior of individual pedestrians in a city to study traffic patterns and urban planning. Non-agent-based simulations. They do not emphasize individual agents and may represent system components as a whole. For example, modeling the behavior of a chemical reaction as a whole without focusing on individual molecules. There are certain key characteristics of simulation. Number 1, modeling. It is the process of creating a model, which is a simplified representation of the real-world system. Models capture the essential features and characteristics of the system while ignoring irrelevant details. Number 2, experimentation. Simulations involve running experiments or scenarios within the model to observe and analyze how the system behaves under various conditions. Number 3, controlled environment. Simulations provide a controlled and repeatable environment where variables can be manipulated, and their effects can be observed without affecting the real system. Number 4, data generation. Simulations generate data that can be used for analysis, decision-making, and optimization. This data can include performance metrics, outcomes, and insights into system behavior. Number 5, iterative process. Simulations often require multiple runs and iterations to refine the model and improve the accuracy of predictions. Number 6, applications. Simulations are used in various fields, including science, engineering, economics, healthcare, finance, and social sciences, to address a wide range of problems and questions. Now let us discuss how to develop simulation models. Simulation models consist of system entities, input variables, performance measures, and functional relationships. The steps to develop a simulation model are: Step 1. Identify the problem with an existing system or set requirements of a proposed system. Step 2. Choose input variables and create entities for the simulation process. There are two types of variables: decision variables and uncontrollable variables. Decision variables are controlled by the programmer, whereas uncontrollable variables are the random variables. Step 3. Create constraints on the decision variables by assigning them to the simulation process. Step 4. Determine the output variables. Step 5. Collect data from the real-life system to input into the simulation. Step 6. Develop a flowchart showing the progress of the simulation process. Step 7. Choose an appropriate simulation software to run the model. Step 8. Verify the simulation model by comparing its result with the real-time system. Step 9. Experiment with the model by changing the variable values to find the best solution. Step 10. Finally, apply these results to the real-time system. There are several advantages of simulation and modeling. With the help of simulation, it is easy to understand how the system really operates without working on real-time systems. Test and make changes to the system and their effect without working on real-time systems. Upgrade the system requirements by applying different configurations. Identifying constraints by performing bottleneck analysis that causes delays in the work process, information, etc. Diagnose problems by understanding all the interactions of complex systems. Additionally, new policies, operations, and procedures can be explored without affecting the real system. At the same time, modeling and simulation have certain disadvantages. Designing a model is an art which requires domain knowledge, training, and experience. Operations are performed on the system using random numbers, hence, it is difficult to predict the result. Simulation requires manpower, and it is a time-consuming process. Simulation results are difficult to translate. It requires experts to understand. The simulation process is expensive.